Alright, John, so this is chapter 16, the last and final chapter that you have to do before you take your Regents, which is awesome. So let's just start doing the information right away. So this is probability chapter. I think that you might have seen some probability in other classes, so some of this might be a little bit of review, but towards the end it's definitely going to be things that you have not seen before. So let's just start right away. Let's see what we have for Ms. Tompkins. The counting principle. Okay, so the counting principle is something that's really easy. It's used when we need to make choices in 2 or more situations and we want the total number of possible outcomes. So let's think about this in terms of a lot of times we do outfits, or I don't know, if you want to go out on a date, you can use the counting principle for those kinds of things. So example number 1. Anthony has 8 different shirts and 6 pairs of pants that go well together. How many outfits can Anthony put together, or whatever? So let me kind of do it for you in this sort of sense first. Maybe you've seen this before where you can do tree diagrams. So Anthony has 8 shirts and 6 pants, I think it was. And we want to see how many different total options that we have. Well, let's think about it like this. We have 8 different options for the shirts that we can make. So the first choice you're going to make is what shirt you're going to wear. So you have 1 option, 2, 3, 4, 5, 6, 7, 8 options that you can make just for what shirt that you want to wear. So you can label this with like 1, 2, 3, 4, 5, 6, 7, 8 if you really wanted to, or you could just leave it like that. Then say I chose to wear this pair of, or that shirt. We did shirts first, I guess. Well, we still have to decide what kind of pants that we want to wear with it. So after you make that decision, there's another 6 possible choices that you can make. So 1, 2, 3, 4, 5, 6, and then if you chose this shirt, you can make another 6 options. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So you can see how like the number of options that you're getting is just growing so quickly that it's pretty annoying to have to do this whole tree diagram for every single question that you have. So we're going to try to think of a different way that we could do this without having to do the tree diagram every single time. Well, if you think about it like this, the first option that you made, you have 8 different choices that you could choose between, and then for the second one you had another 6. So if I went through and counted all these final options at the end, you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, blah, blah, blah. And if you notice something, we actually have 8 different options of 6. So what you really have when you get to your final answer is actually 8 times 6. So instead of making this whole tree out for every single question that you have, if you are dealing with something where you have to choose a bunch of different options, all you have to do is multiply together the number of options that you have. So we have 8 shirts that we are choosing between, and then we're going to multiply that by 6 pairs of pants that we are choosing between. So 8 times 6 equals 48. 48 total options that Anthony could make, or total outfits that he could make given these options of 8 shirts and 6 pairs of pants. So if you're having a hard time understanding that, you could always still go back and make the tree diagram if you want, but in general, in this class at least, we normally just use the whole counting principle theory where you're just multiplying together the number of options that you have. Alright, second example. Mrs. Tompkins is having an ice cream sundae party. She buys 6 ice cream flavors and 12 different toppings. How many different sundaes can you make consisting of 1 ice cream flavor and 1 topping? Okay, so we have 1 ice cream flavor first, so we have 6 total options that we can make there. And then you have 12 different toppings. I really would not like to see the tree diagram for this one because you need 6 branches first and then 12 branches coming off of every single one of those. So instead, I'm just going to multiply these together and get 72 total options of ice cream sundaes that you could make, which is pretty cool to think of. Alright, so that's called the counting principle. It's not too bad. I think we have another question. Okay, so Darren is going out to dinner. There's a choice of 6 appetizers times 4 soups, 12 entrees, and 3 desserts. How many different 4-course meals, 1, 2, 3, 4, could he choose? All you have to do is multiply all those together. I really would not like to see that tree diagram, because especially with that 12 thrown in the middle, that would be really ugly. So 6 times 4 times 12 times 3 is equal to 864 different meal options or meal choices that he can make, which is crazy. All right. Yep. So that's it for the counting principle stuff. I think that you're going to have a couple of questions like that on your homework assignment. I haven't seen too many questions dealing with this on the practice regions exams just because it's really easy. But hey, you know what? You never know. You might see something like that in the future. Next thing we're going to deal with is permutations versus combinations. And I don't really think that you've ever seen this before, but if you look on your calculator, number one, your calculator is going to do the work for you. So I'm going to go through and explain what this is. But first, I just want to show you when you hit the math button right here and then go all the way over to probability. You see how we have an NPR and an NCR right underneath it? Those two buttons stand for permutations and combinations. And I'm going to explain what the N means and I'm going to explain what the R means. But just so that you know where to get that from, that's where you go to find permutations versus combinations. Okay, so you're definitely going to use this in this chapter a lot. Alright, permutations and combinations. What they're really dealing with, what they're really talking about, is if you had a group of items, I don't know, a group of, cell phones. If you had 6 cell phones in front of you, and you wanted to choose 2 of them, and you were going to keep those 2 for yourself. I know this is a really stupid example. So you have 6 of your friends' cell phones out in front of you, and you're going to choose 2 of those, and you're going to keep them for yourself. Well, permutations and combinations, they tell you how many different options that you have of choosing 2. So you have a total of 6 options. How many different ways could you choose 2 of those cell phones? And the difference between permutations and combinations is that in permutations, order matters. Okay, so an arrangement of items in a specific order. Order matters. That's really important. Order matters. And so that just means that, like, if you were choosing cell phones, whichever one you picked up first was more important than whichever one you picked up second. So the order that you chose, I chose this one first, then that one second, it would be different. And then say you chose again and say you picked up this one first and then that one second, it would be a different arrangement. So permutation, order matters. Combination is a selection of items in which order is not important. So order does not matter. And we're going to go over questions like this, and the real struggle with dealing with permutations and combinations is you yourself physically deciding, is this a problem for permutation where order matters, or is this a problem for combination where order does not matter? So the difference between the two, and you're going to see problems like this, like say we had 10 different contestants and they were running a race. Well, clearly, whoever comes in first, you know, they get the first place prize versus whoever comes in second, third, fourth. So in that case, like if you're running a race, order clearly matters. So we would do like a total of 6 runners. How many different ways can we choose, or can we pick 2 winners? Something like that. Order matters. The first person is more important than the second person. in combination, that's more so if I'm picking a group of people to be on my team, okay? It doesn't matter if I choose, you know, John first or Joe first. It doesn't matter because everybody is on the team together. So in that case, order does not matter. So hopefully that helps you a little bit, but we're going to do some examples just so that we can really solidify what I'm talking about. Permutation, okay, see, look it, I already said this. How many ways can 8 students in a race cross the finish line? How many ways can 8 students in a race cross the finish line? And I don't know if I said this before, but you know how we have an N and an R for each of them? Well, the N is the total number of contestants, the total number of people racing, the total number of anything. And then the R is the number that we're concerned with, the number of winners, the number of items that we're choosing. That changes based on what we're actually specifically looking for. So in this case, how many different ways can 8 students, so we have a total of 8 students, how many different ways can they cross the finish line? So because that we're talking about a race, clearly order matters, so we're using permutation. But it didn't say how many different ways can like 3 students cross the race, so we're actually looking at 8p8. Let's see what that is on our calculator. And in order to type this stuff in, it's kind of tricky because you have to type in the n first. So you have to type in 8, and then you go math all the way over to probability, down to p. So 8 NPR, and then 8 again, hit enter. Whoa, and apparently there's 40,320 ways that are possible of 8 students crossing a finish line. So we have a total of 8 kids, and we want to know, you know, in what order could those 8 kids cross the finish line. Now let's look at an example for combination. If 12 students are on a team, how many ways can 5 be chosen to go to sectionals? And in this case, you know, it doesn't matter if who we choose first, it just matters that you got chosen to go to sectionals. So instead of permutation where order matters, over here we're doing a combination. So we have a total of 12 students. How many different ways can we choose? 5 of them. And I'm going to use my calculator again, and it's the same deal. You have to type in the 12 first. 12, math, all the way over to probability, and then this time I'm going to use option 3, which is combination. We have a total of 12. We're choosing 5 of them. How many different ways can 5 students be selected out of 12? And there are 792 ways. And for the most part, you're going to recognize that the number of combinations that you get is typically smaller of a number than if you're dealing with permutation, because with permutation, order matters. So you could do A, B, C, or A, C, B, or A, you know what I mean? Like there's tons and tons of more different ways that you could arrange something if the order matters, if the placement matters. Versus combination where we don't really care what order they're coming in as long as we're choosing 5 of them. Alright, so I think that we're going to do some more questions. Yeah. Okay, so I'm going to stop this right now, and then we can do more of these questions together. Okay?